But yeah, it's lovely to be here to talk to you about the Northern Lights. As you heard, I have a PhD from Imperial College, and I work in fusion energy. But I'm interested in plasmas in general, and particularly the aurora. I love the aurora. I find it a really captivating, wonderful thing to share, and and the sharing is something that I want to talk about later on as well. I think it's really something that brings people together and can be a real connecting piece between people, which I absolutely love. So I'd like to tell you a little bit about my journey to see the Northern Lights, and a little bit about the science of the aurora as well. But to start off with, I'd just like to show you a video of the Northern Lights so that you can see its beauty. But one thing I would like you to take away from this is that the aurora is not just beautiful. There's so much more to the aurora. So that's something I hope to share with you today. The aurora has a reputation for being elusive, which adds to its mystery and attraction. It's a natural process, completely out of our control. To see it, you must be in the right place at the right time. The conditions must be favourable too. The sky should be dark and clear. Clouds mask the view, and even moonlight can wash out the delicate colours of the aurora. To see it in full splendour is a gift. My book, Aurora, investigates the science behind the Northern Lights, but also explores the people, the landscapes, the stories, which are also much part of the wonder of the aurora. As a physicist, my fascination with the Northern Lights grew gradually to a point where I didn't just want to see it, I wanted to know it. I knew the basic science behind the aurora. It is an event caused by charged particles that are channeled down magnetic field lines and interact with our atmosphere. I am fascinated by exploration, particularly polar exploration. I love the stories of people pushing themselves to their limits to increase mankind's knowledge of the world, testing themselves in harsh environments and ultimate survival situations. These delicate lights stirred even those tough men, who often wrote rapturous accounts in their diaries. I wanted to learn more about their motivations and ambitions, both personal and scientific, to different degrees, and I wanted to gain a better understanding of what they endured in pursuit of those ambitions. So that's the aurora, and as I said before, I'm a plasma physicist, and most people look at me blankly when I say that because most people don't know what plasma is. But what about you, ladies and gentlemen? I'm sure some of you know what a plasma is. A plasma is just an electrically charged gas, or it's the fourth state of matter. And you know about the states of matter. You know that we have solids, liquids, gases, and now we have plasma. Plasma is the most extreme state of matter in the universe. It only exists when there's enough energy in the system to strip atoms apart, like this. At such high temperatures, atoms break apart and become a charged gas called plasma, the fourth state of matter. Charged particles are affected by magnetic fields. They spin around field lines. And this spinning around field lines is really important for the aurora, as we'll find out later. Now, you're actually probably more familiar with plasmas than you think, because the sun is a plasma, lightning is a plasma, flames, neon lights, all of these things are plasmas that you're really quite familiar with. And then this here is a picture of the aurora. So what is the aurora? The aurora is a light show that's caused by charged particles accelerated into our upper atmosphere. And the accelerated is a really key part here. This is the scientific part, and this is the piece that people most often miss out when they talk about the aurora. People often talk about the aurora being caused by charged particles from the sun, which get trapped in our magnetic field and cause the aurora. I'm going to tell you in a minute why that cannot be the whole story and why the acceleration is such an important part. So the aurora happens in rings around the poles, both in the North Pole and in the South Pole. But people generally see the northern lights a lot more than the southern lights because there's a lot more land under the northern auroral zone. So this is the area marked here in the red, where in the northern hemisphere you'll most often see the aurora. So you can see that it goes through northern Scandinavia, Iceland, Greenland, Canada, Alaska, and over the top of Siberia. So that's where you're most likely to see the northern lights. And when I was writing my book, I traveled to many different Arctic locations, learning about the people, the places, the landscapes, and the stories of the aurora, because I think that there is so much more to the aurora than just the science. So this is what the aurora means to me, these other aspects. So one of the places that I went was to northern Norway, where I learned about the culture, the folklore, and the early science of the aurora. If you think about the stories and the folklore of the aurora, you find that there's a real spiritual element. And if you ever see the aurora, this isn't really surprising because you really do feel an awe and a gratitude when you see something like the aurora. And in the folklore, a lot of the folklore around the aurora, the stories of the northern lights, you'll find that spirits often come into it. Often there are stories of the aurora being the people's maybe dead relatives or their unborn children. Often these relatives are doing things like maybe they're stirring large cooking pots, and you can see that sometimes in the shapes of the aurora. So there's a big spiritual connection. This here is a reindeer herder that I met in northern Norway. This is Knut, and he took me out one day to see his herd. And over coffee, which he brewed on the fire there, we talked about his experiences of the aurora. And one of the things that he said to me, which I thought was funny, was he said that when he was a child, the aurora were natural babysitters. Those were his words. And he said that the parents would tell their children that they mustn't be home late, otherwise the northern lights would get them. And there are also biblical connections. There are some stories in the Bible that which describe visions of God, which can seem very much like an auroral description, particularly because if you do see the aurora further south, like outside of those rings around the pole in the aurora zone, often the aurora can be seen as more red in color rather than green. And so they're often associated with like fires or blood or like bad omens. And I also loved the stories of the polar explorers going out in the north and the south and seeing the aurora. And they often felt this spirituality as well. And it's funny to think that back then, over 100 years ago, they had no idea what was causing the aurora. It was this man, Christian Birkland, who was a Norwegian scientist, who first came up with a plausible explanation for what caused the aurora. A lot of the early explanations were not very different from the stories, if you like, the fires and the volcanoes and reflections in the ice and things like that. And so Christian Birkland really was one of the first people to do serious research and to come up with a real theory of the aurora. And he did this about 100 years ago. And it's his explanation of the aurora that we still hear predominantly today. He was the person who said that the charged particles from the sun are caught up in the Earth's magnetic fields and funneled to the poles. And he did a lot of research in northern Norway, where he would go up and stay for the winter in in auroral observatories. So this is a small mountain in the north of Norway called Halda. And just to the left of the little peak there, you can see there's a bump on the ridge. And that's an auroral observatory that Christian Birkland had built so that he could study the aurora. And he and colleagues would stay there over winter, and it must have been brutal. It was the north of Norway, it was 24-hour darkness, and they'd be making measurements of the magnetic field. They'd be outside watching the aurora, studying the aurora, noting down the patterns and the shapes and the colors. And apparently they had a big barrel outside that they would sit in because it would shelter them from the wind while they were outside observing the aurora. So it must have been really tough. But yeah, he came up with the this first plausible explanation of the aurora. And I'm going to talk a bit more about that in just a minute. But let's go back to the sun first of all, because the aurora all starts with the sun. Now, the sun has an atmosphere, and that atmosphere kind of bleeds out into space, if you like, and the sun releases something called the solar wind. And the solar wind is just a continuous stream of charged particles, mostly protons and electrons, that's emanating from the sun in all directions. So it's always blowing, if you like, the solar wind. There's always charged particles coming from the sun. So space isn't empty at all. We're in the solar system, we're all sitting in this like sea of plasma, if you like, these charged particles that are coming from the sun. And the sun is very active. It has twisted magnetic fields. This is the surface of the sun, and you can see these magnetic loops coming off from the surface. You often see sunspots where these are very tightly congregated together, and a sunspot is just a darker patch on the sun that we see when we observe it in the visible light. And you also see sometimes these magnetic loops will break and they will throw matter out into the solar system. So just adding to that solar wind. And sometimes you get really big ones, and the really big ones are called coronal mass ejections, and they can throw billions of tons of matter traveling at millions of miles per hour. So they're huge. Now, this solar wind and all these charged particles flying around would actually be dangerous to life. But fortunately, the Earth has protection. We have a magnetic field, and that keeps out the charged particles, because plasmas or charged particles moving through space in a plasma, they also have a magnetic field like this. And magnetic fields can't cross. And so when the magnetic field of the solar wind butts up against the magnetic field of the Earth, it's actually deflected around it. And in fact, it drags the magnetic field of the Earth out behind it, a little bit like a windsock. So rather than a kind of butterfly wing bar magnet kind of pattern that you might be familiar with from making iron filing drawings at school of magnetic fields, which is what the magnetic field of the Earth should look like, it gets stretched out on one side away from the sun, as I said, a bit like a windsock. And so this magnetic environment of the Earth is called the magnetosphere. And it's this magnetosphere which kind of protects us from the batterings of the solar wind. So I said earlier that that basic, it's not really basic, but I mean that idea of Christian Birkland's from 100 years ago that we often hear is still the reason or the mechanism for what causes the aurora that you will hear almost everywhere if you read newspapers or magazine articles, or even if you go up into Norway or one of the northern countries and you get an aurora tour, the person giving you the aurora tour will probably tell you the Birkland description of what causes the aurora, namely that charged particles from the sun are caught up in the Earth's magnetic field and they're funneled down to the poles where they cause the aurora. But I want to tell you here why that can't be the whole story. So if we look at this picture here, so the sun's on the left and the solar wind is coming in from the left. Now, if the charged particles were just going straight in, funneled into funneled into the poles down that region which says polar cusp, then first of all, the charged particles would end up on the day side of the planet. And we don't see the aurora in the daytime, partly because it's too light and you wouldn't be able to see anything. But we see aurora at nighttime. So we know that the particles, the charged particles, the electrons, must be getting around the back of the planet somehow. Somehow they're getting to the back and they're causing the aurora on the night side of the planet. The other thing is that if they were just trickling in, if you like, down, getting caught on the magnetic field lines and funneled to Earth, then they wouldn't have enough energy to cause the bright, vibrant aurora displays that we see. We do actually get something called dayside aurora. So if you happen to be in somewhere like Svalbard, very far north, in the winter when you've got 24-hour darkness, then they do sometimes see dayside aurora. And this is something that they can study. But it's a lot fainter than like the nighttime aurora. So it's very hard to see. So the particles that come in directly don't have enough energy to cause the big auroral displays that we're so familiar with. So something else is happening. And that's all to do with acceleration, as I said at the beginning. So what is happening? Well, this is a video from NASA, and this shows that we've got the sun and the solar wind streaming away from the sun. And when it hits the Earth's magnetosphere, it actually rips magnetic field lines apart, and it drags them over the Earth and lays them down on the tail side of the magnetosphere, pushing the magnetic field lines closer and closer together. But magnetic fields can't cross, and eventually they break and snap. And when they do that, it's called reconnection, and they accelerate particles down the field lines into the atmosphere. And that's what causes the aurora. So this magnetic reconnection and this acceleration, these are key parts of the story of the aurora. This is what is causing the aurora. It's not simply particles from the sun. It's actually particles, those particles maybe originally came from the sun once upon a time, but for a while it's just particles that are out in the magnetosphere, out in the magnetic environment of the Earth, and they're getting accelerated down to the poles. So this is the key difference, this acceleration. So what's happening really is that solar wind is driving a process. Those particles from the sun are interacting with the Earth's magnetic field, and they're energizing it. And all that energy is breaking magnetic field lines and rejoining them in different configurations. And that breaking and snapping and reconnecting of field lines, it's like a bit like breaking elastic bands or something. It's releasing energy, and it's that energy which is accelerating the particles down to Earth. And what's really interesting about the aurora as well is like what we can learn from space by looking at the aurora, because the atmosphere is like a screen that the aurora plays out on. And so scientists can study this, and they can actually find out about things that are happening much further out in space by studying these kind of images. So this is from an all sky camera, which means you're just looking directly up and you're getting a view like all around of the sky. And this is one of the cameras that took that picture, and that's me inside one of the domes. And so now you might be thinking, okay, so the charged particles get into the atmosphere, but what's actually causing the colors? Why are we seeing the colors? So there's a little animation here that tells you about how the aurora is happening in the atmosphere. What happens in the atmosphere to produce the light of the aurora? Let's have a look at one individual atom at about 100 kilometers up. This is oxygen. There's the nucleus in the center, and electrons are flitting around it in different energy levels. But there are also higher, temporary energy levels available to the electrons. Now, if another electron comes in fast from outside, it can knock one of the atom's electrons into one of these higher energy levels. And when it drops back down again, it releases that extra energy it was given. The electron releases it as light. It is this process, happening to billions and billions of individual atoms in the atmosphere, that creates the soft, moving light of the aurora. So that's how that's what's happening in the atmosphere, to cause the aurora. And another thing that's, I think, is very interesting about the aurora is the aspect of space weather. Because the aurora is beautiful, but actually it's a manifestation of a disruption in our upper atmosphere. And this kind of a disruption has consequences. And so space weather, or these kind of disruptions, can cause, for example, power cuts. It can cause currents to be generated in national grids, which can cause power cuts. The fast charged particles can damage satellites out in space, astronauts on the International Space Station, and even flight crew and passengers have to be careful of solar storms, as we call them, because all of those fast charged particles are not good for us. So there's various different things that can happen because of these incoming solar wind particles and these electromagnetic disturbances. And so this is a field called space weather. And this is a picture of me in Canada, in America, in the Space Weather Prediction Center in Boulder in Colorado. And here they use satellite images and data from out in space of the sun, looking at the sun from like different angles and measuring different properties and looking in different wavelengths. And they also use Earth-based measurements as well, like magnetic fields and things like that, to build up a picture of what's happening out in space. And they're able to provide space weather forecasts to people who need them. For example, operators of the national grid, or airlines, or satellites, that kind of thing. So these space weather forecasts are really important to people who are working, or organizations rather, who are working in things that may be disrupted by a solar storm. And something that I find kind of amusing about the whole thing is the contrast between the people who use the space weather forecasts, because the people from the national grid or the satellite operators and things like that, they really don't want a big solar storm, because it's tricky for them to deal with, and it can cost them money as well, because sometimes they have to take things offline until the solar storm has passed, for example. And so they really don't want big solar storms. And then on the other side, on the other hand, you have aurora enthusiasts who are using the space weather forecasts to find out when's the best time for them to go out and see the aurora or to photograph it. And they really do want a big solar storm, because then you're going to get the best aurora displays. So I always find it slightly amusing that you have this huge contrast in the people who are using the forecasts. And so finally, another thing that the aurora means to me is about challenge, I suppose. I really wanted to see the aurora in a wilderness environment, in the way that the old polar explorers would have done. It was maybe a kind of crazy romantic notion, but that's something I wanted to do. And so I decided to ski out across Svalbard in winter, of course, because in summer you have 24-hour daylight and you don't see the aurora. So you have to go out in winter. So this is me skiing out across Svalbard. I went with a guide, and we were camping and skiing, and we were out there for about a week. And I've never been so cold in my entire life. The temperatures went down to almost -40. Everything was frozen. Even in the tent, everything was frozen. You just never defrosted, really. It was a crazy experience. I mean, it's actually one of the hardest things I've ever done, even though it was just a week. And I've also climbed Everest. So these kind of things were comparable. Like this and Everest are probably the two hardest physical things I've ever done, and they're very different. But I did get to see the aurora. Excuse the terrible picture, but trying to take a picture of the northern lights in -40-degree temperatures when you're staying in a tent and all your batteries are frozen and about to die is is not the easiest thing. I have improved actually my photography skills over the years, but I have a lot of respect for the auroral photographers who are able to do incredible things in such harsh temperatures. And particularly if you think about the auroral photographers from 50 years back or more, around Birkland's time, when they were doing things with like photographic plates and like before film and everything. I mean, it's really extraordinary what people have been able to achieve just to see the aurora and to track the aurora. I also, when I was in Svalbard, saw a total solar eclipse, and this was wonderful and like the most incredible way to end a book about the aurora. And it was just chance. I was just so lucky that I happened to be there, like writing the book at that time, that particular year. Because what's so lovely about seeing a total eclipse and thinking about the aurora is that when you see an eclipse, what you're seeing is that the corona of the sun, the atmosphere of the sun, and you're seeing the solar wind streaming out into space. And it's that solar wind that goes on to cause the aurora. So the aurora really is our connection with the sun. It's the way that our planet protects itself from the batterings of the solar wind. It's absorbing all that energy in its magnetic field, and it's dissipating it in an incredibly beautiful light show. So what is the aurora? The aurora is a light show caused by charged particles accelerated into our upper atmosphere. But to me, it's also the people, the places, the landscapes, and the stories. This is what the aurora means to me. And since writing the book, I'd say that that aspect, the stories aspect, has become more and more important to me. It's probably not too much of an exaggeration to say that writing this book changed my life. It brought me new experiences and also new people. I've met so many wonderful people through writing the book, but also since writing the book. I mean, before COVID, I used to give lots of public talks. And one thing I loved most about that was that at the end, afterwards, people would come to me and they'd ask me questions, but they would also tell me their stories, like their own experiences of the aurora. And I always loved that bit. In fact, I missed it so much that this year I decided to start a new community around the aurora. It's called Aurora Stories. And the idea of it is to bring people together and to give them inspiration and connection. And so I provide weekly stories. Sometimes they're personal stories of people's experiences of the aurora, but other times they're science or art or travel or photography or poetry, because I think that there are just so many different beautiful dimensions to the aurora, and so I like to explore the aurora from all these different angles, and the members of course can share their own photos and their stories in the group. So I really wanted to bring together like-minded people, and one day with the ambition of even like being able to do trips together, because one thing that I've realized, again, since writing the book, I've been invited on trips as the aurora expert, and I found that the best trips are always the ones where people have a connection beforehand. I don't mean that they know each other, but like if it's a club, for example, then these people, like I've been on a couple of trips with the Cloud Appreciation Society, as in like, the clouds in the sky, and that's lovely. And people don't know each other necessarily when they get there on the trip, but instantly they have a connection. And so it makes people feel closer already, and it makes the experience stronger, much more so than when I've been on trips which are just run by a travel agent and people just random people mixing together. So it's a completely different vibe when people have a connection. So I suppose I wanted to create a place where people are united by their fascination with the aurora. And so when they do go, if they do go and see a trip together, then the experience will be so much more powerful. So that just gives you a little bit of a taster into what the aurora means to me. As I said, it's the science is fascinating and incredible, and that's like that, and the fact that I wanted to visit the Arctic are the main reasons why I set off on the journey to write my book. But over the period of writing the book and the experiences of writing the book, I found that there's so much more to the aurora, and the aurora actually means so much more to me. It's the people, the places, the landscapes, and the stories. Thank you very much. And if you'd like to, well, I'm looking forward to having a little chat with everybody and hearing your questions and maybe some of your stories. Thank you.
Well, thank you very much, Melanie. That was wonderful. I must say the idea of hiking across Svalbard in the middle of winter is something I'm immensely impressed by. Did you meet any polar bears?
No, we didn't. But we did have to take it seriously, of course. Yeah, it would have been nice to see them, but when you're camping, it could be a little bit scary. But we had to take precautions. So you may have seen, I don't know if you saw on the picture of me pulling the sled, there was a gun, there's a big rifle like strapped to the back. And the guide that I was with, he also had a gun, he had a revolver. So we had firearms. In fact, you're not allowed out of town, you're not allowed out of the capital, like Longyearbyen, you're not allowed out of the town unless you have firearms. You're not supposed to shoot polar bears, of course, because they're protected, but you need to be able to defend yourself. And you also we set up every night a tripwire around the tent, which would set off flares. So we also had a flare gun. So the idea is that you scare the bear as much as possible, and usually they would go away. You'd only actually use the gun in like dire circumstances. So you'd use the flares first and try and frighten them away.
Okay. Well, we seem to be getting some questions, so I will go through them. The first thing is Bill Blackburn has pointed out that we had a talk recently by Jonathan Eastwood on space weather, and indeed it's on YouTube if you look at the Friends of Imperial College site. So I think he's taking it more from the mitigation and protection side. And of course, Jonathan is at Imperial College too. So that's available, but let's, if I can get my, yes. Now there's something I don't know about, but maybe you do, from John Murrell. Can you say anything about the recently identified phenomenon named Steve, which is at a similar height to the aurora, but towards the equator?
So what I can say about it is, I'm not sure if I haven't read things most recently, but I'm not sure if they know the exact mechanism. I think they did do some scientific studies and figure out that it's caused in a different way to the aurora that we generally classify as the aurora, the green band across the sky. And I think it also comes off at a slightly different direction. And so although it's associated with the aurora and it's associated with this disturbance in the atmosphere, it is a different mechanism that's causing it. But what's interesting about Steve as well is that it's something where citizen science really contributed to the breakthrough, you could say, or to the understanding of it, because nowadays a lot of people have cameras, and so they can go out, and a lot of people do just go out and photograph the aurora. And so although Steve is fairly rare, the amount of times and the amount of people going out and seeing it mean that you've got more chance of it coming up. And so it has appeared on various photographs, and people started saying, what is this? This is kind of strange. And I think there's also a citizen science project, you could call it, called Aurorasaurus, like dinosaur, Aurorasaurus. And so if you are photographing the aurora, you can, or if you see the aurora, you can log your sightings, so that then they can build up a picture, like a map of where people are seeing the aurora and what they're seeing. And so I think together they were able to say, we've we're getting all these reports of this thing and we don't know what it is. And so they went to researchers at the University of Calgary, including one of the ones I spoke to, a researcher called Eric Donovan at the University of Calgary when I was writing my book. And so they went and like spoke to him and his group, and they did some like research. They were able to look at, because we've got satellites now, as well as just looking up, there are satellites that are looking down, so that you can actually get different measurements of what's happening in space as well. Anyway, they were able to like go and put all this put all this work together and actually find out quite a lot about this new phenomenon called Steve. And it stands for, I think they called it Steve first of all because of like a character in a cartoon, but then they decided that it stood for something, and I can't remember exactly what it was. It's like emission standard spontaneous thermal emission. I can't remember what it stands for actually, but they do have an acronym now for what Steve stands for. But yeah, I think the citizen science aspect of that is a really interesting one.
Yes, indeed. Um, One thing I noticed, of course, all your movies show it green. You mentioned red. I have a wife who, whenever we've seen the aurora, and we've seen it a lot actually, um, I see it green and she sees it white. This, I think, irritates her immensely. You got any comment about this?
Yeah, that's unfortunately due to her eyes.
They're
It's to do,
lovely.
I know, I'm sure, but it's to do with the intensity. So I think that so if you see a really like low intensity aurora, then people will see it more white, like everybody would see it white. And that's because it's to do with the eyes and the fact that the rods and the cones see different things. And so the night vision ones around the outside sort of see more, they pick up the lower intensity light, but they don't see the color. And the other ones pick up, it has to be higher intensity, but then they do see the color. So if you see a brighter aurora, then you should see the colors. But so maybe her eyes are not so good. They need a higher intensity maybe before um the colored what is the word, receptors like kick in. It's
Okay.
unfortunate, it's very unfortunate for her, but she just needs a higher intensity aurora. So go and see a really bright display.
Yes. Okay. Well, in fact, the question next from Harold Toes, indeed asks about the colours, and sort of why are the colours green is predominant, red, and I believe there's even blue. What does that indicate? What's the scientific explanation of that? And don't tell me it's my eyes, but
It's not your eyes, it's definitely not your eyes. It's actually really interesting, and it's actually very complicated, the different colors. There's a lot more detail about that in my book if you're interested, but the key thing is that there are different colors from different atoms and molecules in the atmosphere. That's the first thing. And this is really interesting because it means that, so well, first of all, we see a lot of green, and that's from oxygen. You can also see the bluey color and sometimes a pinky color as well come from nitrogen. So those are the most like the main constituents of our atmosphere. You also sometimes see a little bit of like maybe pink from hydrogen as well. And so what's interesting from this is that that means that if you look to other planets and you see aurora in space, then you can actually get an idea of the composition of their atmosphere based on like what colors their aurora are, because the atoms release specific colors depending on their atomic structure. So if you remember the animation that I showed you, where the electron gets bumped up to a higher energy level and then drops down, that is to do with the atomic structure of the atom. So that's always the same for a particular atom like oxygen, but it will vary from atom to atom, like oxygen, nitrogen, whatever. So it's like a signature, if you like, these colors that we see. Where it gets more complicated is that different atoms can release different colors, or rather, the same atom can release different colors. So oxygen has, let's say, two different steps energy levels where the atom could go to, and the electron could go to, sorry. And that you sort of saw in that animation as well. Like there's there's one energy level where it will release green, but there's another energy level where it will release red. So the red color actually comes from oxygen as well. The only thing is that you only see you only see the red from oxygen very high up in the atmosphere. So sometimes if you look closely at pictures, or particularly if you look at a picture of the International Space Station, a photograph of the aurora from the International Space Station, you can see this. You'll see that the very top part of the auroral display is kind of red colored, and then the lower parts are green. And that's because the red color is much rarer, and it takes longer for the electron to drop down and release the light. And so that means that there's more chance that something else will just hit the excited atom and cause it to like poof, lose its energy rather than emitting it as light. And so that means that lower down in the atmosphere, where there's lots and lots of atoms like bouncing around, the chances of the red level like staying energized for long enough to actually release that as light is much less. So it doesn't happen low down in the atmosphere. It only happens high up in the atmosphere, where the atmospheric density is so low that there's very little chance of anything else hitting it. So as I said, it is kind of complicated, and I explain it better in the book. But yeah, there are various different reasons why you see the different colors and where you see them in the atmosphere.
I didn't think your verbal explanation was too bad, but
Oh, thank you.
the book must be absolutely brilliant. But okay, next question is, what are the trends in the level of activity over time? Has it got worse? Has it got less? Or auroral activity, is it always the same?
Okay, so that's yeah. So the solar activity or the auroral activity, it generally comes in cycles, in like waves, if you like. So the sun has an 11-year cycle where it goes from being fairly active, and by active we mean that it's probably got lots of sunspots on the surface, which means it's got lots of twisted magnetic fields and like loops coming out, and that means there's more chance of seeing a coronal mass ejection, or one of these big ejections of of matter. And when you get one of those big ejections, you get like more solar wind or more particles coming towards the earth. That's what causes the bigger, better aurora displays. And we just had one actually a couple of weeks ago that was very good. So if you look on Twitter, you'll find a lot of recent pictures from some very nice aurora displays around the 12th of October, I think it was. And so we're now starting to, sorry, so let me go back. So it gets more active, and you get all this like much more twisted magnetic fields and more coronal mass ejections. And then the other side of that is that it actually, the polarity of the magnetic field in the sun reverses. So it kind of twists up, twists up, twists up, and gets to a point where it flips. And then as it flips, it sort of settles down a bit, and you get a quieter sun. And so there's not so many sunspots, and the magnetic field's not so twisted, and you don't get so many coronal mass ejections. You get some, but not so many. And so that's like a low point. So we call that solar minimum, and we call the high point solar maximum. And so generally you get more big aurora displays around the solar maximum years, and you get fewer around the minimum years. You still see the aurora because, as I said at the beginning, there's always a solar wind. So there's always some kind of, base level aurora, if you like. And there are also things called coronal holes, which are just areas in the sun where they release a lot of fast particles, and these can produce nice aurora as well. And so you can get those. So it's not like you see no aurora around the minima. You do. It's just you generally can see more bigger active displays around solar maximum. So yeah, this is an 11-year cycle. So now we're kind of ramping up again now. We've had solar minimum, and now we're sort of building again towards solar maximum. So people are quite excited about that.
Okay, I'm going to actually ask John Murrell if he'd like to give his own question. Oh, he says not a question; it's more a commentary, because John has the a little more about Steve's. He knows much more about them than I do, and possibly you. So, John,
Great.
would you like to unmute yourself and tell
Yep.
us?
Yeah, I've only just been following it from what's on the internet, and there's actually quite a good Wikipedia page on it. Apparently, it was discovered as the original researchers called it a proton arc, but apparently protons don't emit visible light radiation. So the researchers told them, you can't call it a proton arc, so they called it Steve, as Melanie said, after the cartoon character. And the researchers were then left with a phenomena with a rather strange name and had to reinvent a backronym, would you believe? Horrible word, which is strong thermal emission velocity enhancement, which is sort of a horribly muddled up word to try and make Steve, but that's what they did. They were very lucky because the Swarm mission, but you probably know more about that than I do, David, flew through the arc shortly after it was sort of identified, and they found that it's got very high temperatures and very high velocities. We ought to have a talk on it if we can find a researcher who's...
Yeah, no, I certainly know the Swarm mission. It was one of my babies when I was working with the European Space Agency. So, yes, okay. Well, thank you very much, both for your own research there, John, and enlightening us all. Very interesting. Steve's our strong thermal emission velocity enhancement, if you ever need to stop conversation at a party. And I very much thank you, Steve, for bringing that up. I'm now going, I think, Melanie, I let on that you're actually working in controlled nuclear fusion now. And I think this question is almost exactly for you. It's very controversial, comes from John Talbot, because I believe your company, the company you work for, is looking at sort of small fusion reactors, but maybe I'm wrong. But I'm going to let John unmute himself and pose your question to Melanie. John?
Is this working?
Yep,
Yes.
we can hear you.
Yes. Where is it? It's disappeared off the screen. I was present at your talk on fusion a while back, and I remember that. And I don't know too many fusion physicists, so I thought I'd take the opportunity of being in front of one and ask this question. And it relates to what I read in the press last week, that the UK is planning to build a working fusion reactor somewhere. They were discussing whether it was going to be in Culham or in Scotland or somewhere. And I'm also aware of the ITER reactor in the south of France. And it's plain for anybody who watches ITER at all that it is an absolutely massive undertaking with a vast budget and a very big head start. And I wondered if you knew what it was that persuaded the UK that it could take on what is essentially the global physics community and compete with something as big and as powerful as ITER. I wondered if anything had changed, or whether you knew, for example, what kind of reactor the UK was planning to build.
Thank you. It's I don't think it's about the UK trying to compete with ITER. I think it's more about the fact that we need clean energy solutions, and it's getting more and more urgent, and so countries need to start doing research. Well, not doing research, we're already doing research, but I mean moving from the lab to the commercial space. And that's what's really exciting about now at the moment. We're really seeing that transition start to happen. In fact, the UK government at the moment is very supportive of fusion. They just released a fusion strategy a couple of weeks ago, where they said they want to be like the first country to commercialize fusion. You know, they're really trying to take the lead on this. They're developing a regulatory framework as well, so that companies have certainty and industry have certainty when developing pilot plants. So I wouldn't say it's about competing with ITER. In fact, the UK is part of ITER. We contribute to ITER, and the UK runs the JET Tokamak, which is at Culham, and and that's a European machine, and that's been doing research since, well, for most of my lifetime actually, since the early 1980s, and it's currently doing research that contributes to ITER. In fact, so much of the research that's been done around the world so far on fusion has been kind of contributing to ITER, and even the private companies that are now springing up, many of them, particularly the ones that are based on the tokamak concept, are building on those foundations, those research foundations. And so I think that it's definitely not so much about competition. It's about how much, like, what we can learn from these different research strands. But there is a feeling now that we need to start doing things faster, because ITER has been very, very delayed, actually. Like, we should have, JET got a world record in fusion power production back in 1997, and it would have been nice to have a new machine soon after that to be doing research, like over the past 20 years. But instead, because ITER is a worldwide collaboration, it's very big, it's very bureaucratic, it's very political. It's taken a long time, unfortunately, to get it agreed upon and then built, now the construction. So it's in an exciting phase now where it's actually the machine itself is being built. The magnets are coming in. We're seeing huge components from around the world coming in. But ultimately, it's not going to start operating till probably the late 2020s. It's not going to get anywhere near getting past energy break even, more energy out than in, until probably the late 2030s. And I think there's a consensus now that we need to be pushing faster and harder on these things. So yes, the UK is committed to building a power plant, or a pilot plant will be the first thing. It is a slightly different technology in that it's the same kind of concept. It's a tokamak concept, but it's a bit more squashed up. So it's what's known as a spherical tokamak. So instead of being like a donut shape, it's more like an apple, kind of squashed up. And that has advantages in that it can be more efficient. And so we think it make a better power station. It also has challenges. It's more squashed up, so it's harder to engineer. There's less space. But that's something that the UK has really been pioneering. And the company that I work with, Tokamak Energy, is also pursuing a spherical tokamak concept and using advanced magnets made of high temperature superconductors to do that. So I think it's a really interesting time at the moment. There are a lot of private companies coming into the space, and people are really starting to think about not just how you can get the fusion reaction happening in the in the center of the machine, but also what needs to be done next to actually get to a commercial power plant. So I think it's a really exciting time at the moment.
Thank you.
Thank you.
Well, I think that was, I'm a little bit older than you, Melanie, but I fell in love with plasmas back in the, 60s when I was an undergraduate, and thought, I didn't know whether to do fusion in the lab or whether to go into space. This was in the 60s. I have to say, fusion was going to be well inside my career, 20 years at the worst. I've got to say, it's still 20 years ahead of us. I am so glad I took the trip to space. But, I probably shouldn't say that. It's not really fair. But it is quite exciting to hear you talking that way, because an old cynic like me just thought, well, we'll go on trying to build a reactor forever and ever. It's always 20 years away. Well, you sound much more optimistic than that, so good for you.
Well, yeah, I suppose I am a bit of an optimist anyway, but it's true. It's always, that's the joke. It's 20, 30 years away and always will be. I hate that joke, but I think it's one. There is actually some research from there was a paper from America. I think it was back in the 70s or the 80s, where they looked at fusion budgets and they gave some projections for like what they thought would be necessary, like budget wise, to get to fusion on particular timescales. So there was one scenario which was a bit like a Manhattan Project or something like that, or Apollo, where you could just put in lots of money. So basically there's like no holes barred. You can do whatever research you want. You can do things in parallel. And I think they then predicted that you'd be able to get to fusion by, well, like before the year 2000 anyway, or around then. And then there were other scenarios where you could say, okay, so maybe you can't have all the money that you need. Maybe you have to do some things in series or in sequence rather than in parallel. So then it's going to take a bit longer, and maybe you'll get there by like 2010. Anyway, there was another level, which is like the very basic level was you provide enough funding for like basic scientific research, and you keep it ticking over. And that scenario never gets to fusion. It's just like you drip feed the fusion program and you never get there. And you know what the funding has been since the 1970s? It's been that baseline scenario. They've basically drip fed the fusion program for all that time. So what we really need is an injection of cash. And of course, you need people who are like, you know, smart young people coming into the fields and driving it forward as well. But that's another reason why it's getting exciting now, because over the past 10 years, you've been seeing private investment coming in, and it's fairly small in comparison to like the government funding at the moment. I think to date, there's been about $2 billion invested in private companies. It's quite a big number, but they're still going to need more if they're actually going to get to a working commercial fusion power plant. So that's the thing. Yeah, I believe that it has taken a long time, but the program has been drip fed for decades. And if we really see an injection in investment, and now with the renewed drive, or not renewed drive, but you know, there's much more increased desire because of climate change targets and things like that. So yeah, it still might take most of my lifetime too, and I wish it wasn't the case, but well, it is. So
I'm sure it's going to take more than my lifetime. That's fascinating insights you've given us there. I think I'm going to have to wrap up now, because you've certainly we've worked you hard, I think. You've done your full hour, and it's been a wonderful, your enthusiasm, I think, came across very effectively. And I'd put you in the explorer category. I mean, that the idea of trekking across Svalbard in the winter, I'm going to carry with me. And I also love the way, and I imagine most of the audience did, you sort of just said, oh, and I climbed Everest. I mean, I hope you weren't looking for the Aurora on Everest, because I assure you it doesn't go there very often. Once a century, I think. But
I just have a thing about combining science with adventure. I think I see science in the landscapes that I love, and I love skiing, I love mountains, and so I'm attracted to those places. And then I see science stuff and I'm like, well, that would be interesting. And like I got interested in the physiology side of Everest, and I like the exploration aspect as well, like how these people have been able to, you know, push those boundaries and do those things, whether that's climbing Everest or getting to the poles, or, you know, deducing what's behind the aurora. So yeah, I'm just fascinated by those kind of things.
Well, I think that's wonderful. I think it's been wonderful to listen to you today. And then you'll wrap up on fusion, which of course is your real professional interest at the moment. That was also extremely interesting for all of us. I think we all do care about climate change. And of course, some of us, we had a virtual trip to Cadarache, to ITER, a couple of months ago. I think it's one of the best trips I've been on. And it was virtual. I'm just longing to go down there and see it. It looks truly dramatic. It's so... Okay, I think I really do have to wrap up now. And I think if everybody wishes to unmute, then we can show Melanie our appreciation by putting our hands together.
Right.
Melanie, thank you very much.
Thank you.
I'd like to conclude by saying that our next talk is from Professor Shattock. Is that correct? Yeah. Sorry, I thought I heard some objections there. Professor Shattock, the 20... Sorry, I've lost my notes at that point.
It's on the 28th of October.
Yeah,
David.
didn't want to do it from memory either. 28th of October, and the title is Developing Novel RNA Vaccines for COVID-19 and Future Pandemics. Well, I have to say, if Melanie made me optimistic, the idea of thinking about future pandemics makes me less than optimistic. But anyhow, can I say thank you for everybody who's come today. It's been great having you here. I hope you've enjoyed it. And thank you again, Melanie. And see you next week for Professor Shattuck's presentation on October the 28th. And I'll remind you, we all love this activity. If you have the capacity to make a small contribution, it will be gratefully received by friends of Imperial College. All you need to do is visit our website. And thank you very much to those of you who have done that recently. We've had a real burst of gifting, and I'd like to say thank you to you all. It's very important to us as we approach meeting again in non-virtual circumstances. I'm longing for it, and I hope some of you are too. Okay, so this is the beginning of the weekend. I wish you all a very good weekend and see you soon. Okay, cheerio.